great overview of NASA Earth Science. It's my pleasure now to introduce the division director of our astrophysics division, Dr. Mark Clampin.
Okay, good afternoon, everybody. I'm going to be talking about NASA's astrophysics program and what we're looking forward to as we go forward into the next year. So you heard about the golden age of space science. We have a big golden telescope, and that's the Webb Space Telescope. And I wanted just to show a couple of results from Webb this year that kind of point to where we're going next year. So this is an image of a lens cluster, and you can see all these white galaxies in the foreground here, and they're basically demonstrating a theory that Einstein first proposed, which is that large mass bends light. And so this cluster of galaxies, the white ones, are actually bending light coming from more distant galaxies behind them, which you see as these distorted wisp-shaped patterns. And this is a really important result because in this particular galaxy, which is, of course, heavily distorted, you see three different point sources here, and these are the same image. They're basically a supernova that is triply lensed by the bending of the light by the foreground cluster. And this is a really nice result because we can use the time delay, the brightness of the supernova, and the gravitational lens model from this result to get an independent measurement of the Hubble constant. And one of the big issues in astrophysics right now is what's called the Hubble tension. And the Hubble tension is the disparity in the value of H naught as it's been measured by the European Planck mission looking at the cosmic microwave background, and the Hubble constant as it's been measured by studying supernova and also studying Cepheid variables. So there's a discrepancy, and a lot of people have said, well, it probably doesn't exist and it's just measurement error. But in addition to the result by Adam Rees earlier in 2024, this also confirms Rees's numbers and demonstrates that there really is a discrepancy between the two values. So that's telling us there's something wrong with our understanding of the value of H naught and how we're reaching that conclusion. So this is a great result. It also demonstrates the ability the Webb has to really see back all the way to the very first galaxies that formed in the universe. And I told people at a meeting yesterday, we've kind of got out of what I call the wow period with Webb, and people are really starting to look at all the results we're getting on the early universe now and starting to try to pull all that together and understand what they're telling us. So I think we're going to see a lot of new insights this year as people really get to grips with what early cosmology is telling us as we look at data from the Webb Space Telescope. Webb is also doing a great job in general astrophysics, looking at a range of different science problems from the formation of stars to the formation of planets, and also studying the atmospheres of planets around other stars. And this is a good example. This is an exoplanet called WASP-39, very imaginative name. And what you're seeing here is the thermal difference between the morning terminator of this tidally locked planet and the evening terminator. What this is showing us is that there's some pretty extreme climate on this exoplanet. So Webb is spending more and more time helping us understand the rich diversity of different kinds of exoplanets orbiting other stars. And people are just starting to do the really tough measurements, looking or trying to find the atmospheres of small rocky planets and possibly to characterize them. So we expect a lot of really great new results this year from Webb. So let me just spend a minute talking about the astrophysics fleet. The purple missions here are what we call our missions in extended operation. We have 3 missions in prime operation right now: Webb, Euclid, which is a partnership with Europeans, and also CRISM, which is an X-ray spectroscopy mission. And then we have all these missions down here, which are either in formulation or are actually being built. So this year we will launch SphereX, and I'll talk about that in a minute. And I'll also talk about Roman, which will launch in 26. Coming on later, we have a couple of new small explorers, and we just recently selected our first astrophysics probe candidates. We selected 2 missions, and we'll down select in 2026 to one of those missions. And this is a new mission line that was proposed by the Decadal Survey. So let me talk a bit about SphereX. SphereX will launch at the end of February, and it's designed to do an all-sky near-infrared survey spectroscopically. So it's doing a form of hyperspectral imaging, which should be familiar to us scientists, and it's going to map the whole sky. And the goals of this mission are to understand the early universe, understand how galaxies formed and evolved, and also map out the spectroscopic signatures of regions of star formation. It's a near-infrared mission, so it has to be kept, pretty cold. So this is why you see this very strange trumpet-looking assembly. These are shields that allow the central telescope and the sensor systems to cool down to temperature. This mission is pretty much completely finished now. We'll be putting it on a truck early in January and shipping it out to Vandenberg for launch. So this will be really exciting. Then I want to talk about the progress we've made this year with the Roman Space Telescope. So Roman is our next big NASA flagship, and it's a major departure from what we've done in the past on NASA flagships. So if you think of the Hubble Space Telescope, the Webb Space Telescope, or Chandra, these are all basically point and shoot missions. You write a proposal to look at a particular target in the sky, and you're funded to do the research. Roman is our very first mission designed as a flagship to do surveys. Its primary science goal is to understand the nature of dark energy, which is this force that we don't yet understand that's making the universe accelerate as it expands. And we'll be conducting a number of different studies, such as looking at extremely high redshift supernova, trying to look for baryonic acoustic oscillations to try and elucidate the nature of dark energy. So this is the core goal of this mission. But it's a near-infrared survey mission. It's got the same angular resolution as the Hubble Space Telescope. It will basically go as deep as the Hubble Space Telescope in its survey, and it will cover a very large region of the sky. So we will be able to do all sorts of science, such as following up gravitational wave counterparts, mapping dark matter, as I've already said, understanding the evolution of the universe, how galaxies have evolved over time, study stellar populations, and also to really understand the distribution of exoplanets in planetary systems. So up until now, most of the work we've done studying exoplanets has really focused on transits, which are relatively short period planets that orbit close to their star. So we don't really know that well what the distribution of exoplanets are beyond basically where Earth and Jupiter are in our own solar system. So using microlensing as a part of this survey that the Roman Space Telescope will do, we'll be able to really map out the outer regions of solar systems and understand where we should be looking for habitable planets, and also what solar systems really look like. Roman is making great progress. So this mission is cost capped by Congress, and our job is not only to do great science, but also to bring it in on cost and budget. And we are making great progress there. So as of a few days ago, Roman telescope, which you're seeing here, was delivered to the Goddard Space Flight Center, and it's now being integrated into the spacecraft. And we are looking at a late 2026 launch for this mission. Roman is going to be a real game changer. The other big change for astrophysics is that this is one of our first petabyte scale missions. Now, I know for us scientists, large data sets are sort of day-to-day thing for you guys. But for astrophysics, this will be one of our first really big missions that produces petabyte scales of data. And so we're in the process of working with our science community to explain to them how we are going to be moving from individual computing to working in the cloud and doing cloud computing on these very large data sets. We're also changing the paradigm for how people decide what to observe. So we've basically gotten very large community groups to work on defining 3 very large surveys, and people will apply for grant money to actually study the data from these surveys as we go forward. So I'm going to finish up by talking about the Habitable Worlds Observatory. This is our next big flagship that was recommended in the 2020 Decadal Survey. And we were told by the Decadal Survey to basically design a telescope that would conduct a program of general astrophysics and which would survey nearby stars for habitable planets that we could then study to look for biosignatures or evidence of life. So this year we've seen a rapid acceleration of our work in this area. We were directed by Congress to create a project office at the Goddard Space Flight Center, and we are moving forward with that project office. Their first goal will be to map out the technology that we need to do this measurement. So in order to be able to observe a small habitable planet similar to our Earth, we need contrast levels of around 10 to the billion. So that's a really tall order for a chronograph. It also requires that our telescopes are stable at the level of tens of picometers. So this is, factors of 100 beyond the performance that we currently have with the James Webb Space Telescope. And as I said, not only will it conduct a program of exoplanet science looking for habitable planets and studying whether there's evidence for life, but we'll also conduct a very broad program of astrophysics. Every NASA flagship for astrophysics is an observatory, so we're not just doing our primary science goal, but we have an observatory that can undertake a very large and diverse range of disciplinary studies. So for the Habitable Worlds Observatory, we expect that large aperture and UV and visible capabilities really allow us to study things like galaxy growth, the evolution of elements over time, and study solar system objects in a lot more detail in the ultraviolet. So I will finish there, say thank you.